Hello, class. I am going to do the first lecture from section 8.5, really. Yeah, it would be around section 8.5 to about 8.7, I think, or something like that. Somewhere around there. I'm not sure exactly how far I'm going to get in today's lecture, but we'll sort of start out there. You know, one thing that I wanted to mention is the pointing vector. The pointing vector is E cross H for the waveform. And of course, the units that this is in is watts per square meter, right? So if I wanted to change that, we know that watts are kilogram meters squared per seconds cubed. And of course, meters squared is meters squared. So those cancel out. And that gives us kilograms per seconds cubed. So that would be the units of the pointing vector. And is that right? Let's see, watts per square meter. Yeah. But what this really does is it points the direction of the movement. So if you go E cross H and you take, you know, the electric field and you cross the electric field, let's say the electric field is in the x-axis, and the, oh, I'm sorry, you can't see it. Well, I guess, well, let's say that the electric field is let's just look at a waveform here. Let's say that the electric field is going like this, right? And the magnetic field, that would be in the x direction. And the magnetic field then is going like this. I don't know if you can see that because I haven't really hashed it out or whatever. But this would be the one that you would see here, and then you'd see that, and you know. So anyway, what I'm saying is that the H field is going perpendicular in the y direction, and the E field is going in the x direction. So if we said that, if we had E I hat crossed with H J hat, then what would we get, right? Just look at our little thing here. Oops, sorry. I, J, K. So we got IJ equals K, and there we go. So K hat is the direction that it's going in. So the waveform is actually propagating in that direction. So that's what I wanted to point out, really, what the pointing vector is all about. No, it's not spelled P-O-I-N-T. It's not pointing in the right direction. His name just happened to be pointing. So the pointing vector tells what direction the waveform is propagating in. And I just thought that I would mention that. Now, what I wanted to get into was the reflection coefficient and standing waves and everything else. And so that's where I want to go for today's lecture. Let's just cut that section off, just as sort of an interesting thing. So when we talk about the reflection coefficient, the reflection coefficient for voltage and the reflection coefficient for current are different from one another. And so I'm going to give you both of them right now, and I'm going to give them to you really in the real form of what we would have. So the reflection coefficient for voltage is the line voltage minus, or the load voltage, I'm sorry, minus the characteristic voltage divided by the load voltage plus the characteristic voltage of the line, right? Now, if we were looking at the reflection coefficient for current, the reflection coefficient for current is the characteristic impedance minus the load impedance divided by the, well, I could say the characteristic impedance plus the load impedance, which is the same as what it is over there. And you can sort of see that this is just going to be 180 degrees out of phase of this one, right? You know, 3 minus 5 is minus 2, and 5 minus 3 is positive 2. So I think everybody can see that we've really got the same reflection coefficient, but it's going to be opposite. And we'll do a little example of that to show that it's 180 degrees out of phase between the reflection coefficient for the voltage and the current in just a little while. I'll just so to give you portents of the future. But I also want to point out what the general equation is. This is really the equation just dealing with the real part of the reflection coefficient, but the reflection coefficient is actually a complex number. And if I wanted to find out what the impedance was along the length of the line, because it's changing, then the actual equation is the characteristic impedance of the line times the load impedance plus the characteristic impedance of the line times the hyperbolic tangent of the propagation constant times the distance along the line that you would be going. And all of that divided by the characteristic impedance of the line plus the load impedance times the hyperbolic tangent of the propagation constant times the distance along the line. That's the actual general equation, right? And then we're going to use some assumptions to make this equation a little smaller. And of course, when we're talking about then we're talking about the full thing, not the lossless line approximation. And so when we're using this general equation, we're assuming that we're using the equation for the complex propagation constant, right? Alpha plus J beta. And we know that the equation for that, if we're using all of the constants in there, would be R prime plus J omega L prime, that's an L, times G prime plus J omega C prime. And of course, in graduate school, you'll be using numbers for G prime, although G prime really is 0 pretty much all the time. And you know, things will change. You'll be looking at this, but and this is the but. So this is the complex propagation constant, right? And we would use that in the general equation. But if we make an assumption, so here's the assumption that we're making. We're going to make the assumption that R prime equals 0 ohms per meter and that G prime equals 0 mhos per meter, right? So it's a lossless line approximation. It's our lossless line approximation that we're going to use there. And if we do use that, then we know this. We know that alpha equals 0 nepers per meter, don't we? Because in the lossless line approximation, if R prime is 0, then alpha has to equal 0, right? If R prime is 0, alpha has to equal 0. So what that does is that changes this, doesn't it? It makes it just an imaginary number. It makes this an imaginary number. So that's what we can do. We can replace this with an imaginary number. And so what we get then is we get the simplified form that z at a distance x along the line is just going to be z0, just like it was over there, except now we can change this fraction that we had before, And we can say that it's just the load impedance plus J. That's right, it's J, because now we're only using this part of the equation, aren't we? You're only using J and beta. So it's Z sub L plus J Z sub 0, the characteristic impedance of the line, times the regular tangent of beta times x. And it's only beta because there's no alpha anymore. Alpha equals 0, right? That's right. And that's all divided by Z sub 0 plus J times Z of the load times tangent of beta x. So you can see that it's quite simplified for that, right? Because we've really now taken it off the hyperbolic tangent. We've just got the regular tangent. But you know, let's look at this equation. Let's just look at this equation. Let me just circle that equation there for a second, and let's look at that equation for two specific boundary conditions. First of all, I want to look at it for an open circuit. And when I say open circuit, what do I mean? I mean that the load then is going to be infinity and beyond. Infinity ohms is going to be my load, isn't it? So that's for the open circuit. So let's just cut off a section here for the open circuit. And then I also want to look at it for a short circuit, right? That means that I take a piece of wire and I short out the signal wire to the ground shield, right? So I'm shorting the load. And so then my load is going to be 0 ohms, right? So two different situations that we've got here. Let's look at how it plays out in this equation. So if we say, let's just see if we've got well, actually, I'll do this one. I'll do the open circuit first because it's a little more difficult, and then that makes the short circuit seem so incredibly easy. Why didn't you do the short circuit first? All right, let's do this one. So we've got Z sub 0, right? And then Z sub L is infinity. So we've got times, let's just make our fraction here, infinity plus J. Does it really matter what Z sub 0 is, or tangent beta, or that? It's really 0, isn't it? Right? Because anything compared to infinity, I don't have any infinity in here. So this is infinity, and so I have no infinity in here. So that's 0. And then on bottom, what do I have? Well, I've got Z sub 0, so that goes there. And then I've got plus J infinity, don't I? Is that what I've got? If I screwed this up, let's see. Infinity. Oh, I'm sorry. Infinity tangent beta x. I forgot my tangent beta x. Excuse me for that. All right. So now what do we have, and how can I simplify this a little bit? Well, I'll tell you what. Z sub 0 plus J infinity tangent beta x, that really is going to 0, isn't it? So what I really have is I really have infinity divided by J infinity times tangent beta x. And I think you can see the infinities are going to cancel out there, and that's going to give me Z of x equals 1 over, I'll do this in a couple steps, J tangent beta x, right? Now, what is J? What is 1 over J? I think everybody knows 1 over J is minus J, right? Everybody can do that. 1 over J is minus J. Let's just do that. So if I've got 1, I've got 1 at an angle of 0. 1 over J. J, what's J? J is 1 at an angle of 90, isn't it? So 1 divided by 1 is 1, and 0 minus 90 is minus 90, right? So what is 1 at an angle of minus 90? That's minus j, isn't it? So you can all see that that's what it is. And then, of course, 1 over tangent beta x is just cotangent. So I've got minus j cotangent beta x, right? So this is what the impedance, how the impedance is going to change along a line that is an open that has an open circuit at the end of it. That's how my impedance is going to change. Now let's look at a short circuit. If we look at the short circuit and use the same equation that we had over there, z sub x then is going to be z sub 0, and then now z sub l is going to be 0. It makes it so much easier, doesn't it, for you to see? Although you know, I don't know why. 0 and infinity, 1 over infinity is 0. So I've got 0 plus j times z sub 0 times tangent of beta x, right? And then in the bottom, what do I have? Well, I've got z sub 0 in the bottom plus j times 0, right? Because j times 0, that's what z sub l is, times tangent of beta x is just equal to 0. So I really have z sub 0, right, is gonna cancel out with this z sub 0 in the bottom because that's just 0. And so all I'm left with is j times the tangent, right? You've got a negative j, cotangent beta x. You've got a positive j over here, tangent beta x. All right? So that shows how the impedance would change along a line that is either open circuit or short circuited at the end of the line. Thereby the load impedance that we have at the very end is either infinity or 0. Infinity for an open circuit, 0 for a short circuit. All right. Okay. Now that's really the impedance along the thing. You're going to see where that comes into play with the reflection coefficient and how the reflection coefficient would change along the length of a standing wave as well. Anyway, I forgot to put the time on to see how long this lecture was, but I want to show you a couple things. Let's say that let's just do an example here for a second. Let's say that I had a characteristic impedance of a line that was 17 plus J10 ohms, right? So it's a complex number. So that's my characteristic impedance of my line. And then the characteristic impedance of my load is going to be 15 plus J26, right? Ohms. So it's a load that is both resistive and inductive. Do you see why I say inductive? Because it's positive J26, not negative J26, which would make it a capacitive load. Negative is capacitive, positive is inductive, and of course the 15 is resistive. So that's what I've got. I've got a line like that. Now, what's going to be, if we've got those two things interacting, that load and that line, what's the coefficient going to be for the voltage and for the current? Well, the reflection coefficient for the voltage, just like I've got it up here, is going to be my load, my load impedance, which is 15 plus J 26, right, ohms, minus my characteristic impedance, which is 17 plus J10 ohms. I'm not going to put ohms on all of these things, but you can follow along with me. Then, if I'm going to add these two together on bottom, well, 15 plus 17 is 32, and 26 plus 10 is going to be 26. So on top, I've got 15 minus 17, which gives me minus 2 plus J16, right? Because 26 minus 10. And then on the bottom, of course, I've still got my 32 plus J26. And if we turn those into phasors, I'm going to do that for you. That would be 16.124 at an angle of 97.125 degrees. And then on the bottom, that would be 48.17 ohms at an angle of 48.37 degrees. Okay? Just so that you can see that, you know, what I'm doing, how I'm dividing it. And of course, I think everybody can see that what we get here, if we divide these two, 16.124 divided by 48.17 gives me 0.335 at an angle of 48.755 degrees, right? So that would be my voltage reflection coefficient. And now if we do the same thing that we've done here, but instead of for the voltage, we do it for the current, right? So if we're doing it for the current, what would be upside down? Well, this would be backwards, wouldn't it? And in fact, instead of this being 17 or 15 minus 17, like I've got here, I would have 17 minus 15, which would give me a positive 2 and a minus J16. And so if that was positive 2 and minus J16, it would still be 16.124, so I'd still have the 0.335, but instead of it being 97.125, it would be minus 82.182. So let me just write this here. So if we were doing the current coefficient, we'd still have the 16.124, but the angle would be different. It would be minus 82.8 degrees. And then we want to divide by exactly the same thing, the 48.17 at an angle of 48.37. And what we would end up getting for the current reflection coefficient is going to be the 0.335, but then the angle is going to be minus 131 degrees. And you can see that the 48 degrees and the minus 131 degrees, it's actually minus 131.2. So you can see that those match up to 180 degrees, and that's what it is. The reflection coefficient for the current and for the voltage are off by 180 degrees. And I just wanted to do that sort of as a little example here. I'll just put example right there. And I'm going to start from there. We've still got a couple lectures to go. I want to talk about, you know, standing wave ratio and things like that. And so when I get done, I'll be done. It's not far away, but I want to cover this area, and I want to do an example using the Smith chart to have a parallel stub matching and show you how to do a parallel stub matching with the Smith chart. Okay, that holds us for lecture 44, I guess. Okay, see you in the next lecture.